solving and modeling. Now, some log equations can be solved by changing to exponential form, as you saw in example 5, section 3.3. For other equations, the properties of exponents or the properties of logarithms are used. A property of both exponential and log functions that is often helpful for solving equations is that they're one-to-one functions. Now, all that stuff, you guys got to remember, an exponential function passed the horizontal and vertical line test. That tells you it is a function, and its inverse is also a function. That tells you it's one-to-one. All right? So it's just telling you, for any exponential function, if b to the u equals b to the v, then u equals v. So if they have the same base, the exponents are going to be the same. And if log of u to the base b and log of v to the base b, these will also be the same here. Okay? Now, example 1 shows how the one-to-oneness of exponential functions can be used. Examples 3 and 4 use the one-to-one property of logarithms. Now, today we should get through example 4. I may not do all the examples, all the parts of the examples, but we should get through example 4. Now, in order to do example 1a, it's actually super simple. We need to get 1/2 x to the third by itself. So how are we going to get 1/2 x to the third by itself? Or x divided by 3. We're going to divide by 20. Five divided by 20 is 1/4. Now, can I rewrite 1/4 as something with 1/2 to a special power? Can I rewrite 1/4 as something with 1/2 to a power? 1/2 to the second power. Now, really what we're using this top one. We have the base to a power equals the base to a power, then the powers will equal each other, the exponents will equal each other. So we can say then that x over 3 is equal to 2, not 6, because the answer will be 6, is equal to 2. That means then x will equal 6. All right? So we'd have here, if we put this back into the equation, 1/2 to the 6 over 3. Well, 6 over 3 is 2. What's 1/2 squared? 1/2 squared would be 1/4. 1/4 of 20 would be 5. Okay? Now, I'd like you guys to work on B at this time.
Are you recording?
Now, if we look at this, I can rewrite this as 1/3 x to the third will equal 1/9, which means I can rewrite 1/9 as 1/3 squared, which would mean x over 3 will equal 2, which means x will equal 6. Now, it just so happens that this answer is equal to 6, just like the last. Yeah.
Are the bases always going to be the same?
They're going to make them like that, yes.
It's always.
Yeah, on problems like this, they're always going to make them nice numbers for you guys to work with.
Okay, and it equals to like x.
Yes.
X over 3 is that because they're both x?
Yes. They both have the same base, so the exponents are equal. All right? Now, example 2 is a little bit more difficult. You might need some more paper. You might need some more room on this. I apologize, but that's the nature of the beast. So, the equation example 2 involves the difference of two exponential functions, which makes it difficult to solve algebraically. So we're going to start with the graphical approach. Doesn't mean we're not going to solve it algebraically. Just we're going to start graphically. So put this in your calculator. Parenthesis e to the x minus e to the negative x divided by 2 is equal to 5. Now zoom 6 it, and you'll see what happens. Huh?
Where are you doing exact? We don't have to listen to it. Oh.
Are you good, Kelsey?
No, I got it.
All right, if we find our intersection, so second trace, go down to number 5. Find our intersection of 2.312. So intersection is about 2.312. That's the number that we need to get to. All right. Now, if you got an intersection with something different, check to make sure your entire numerator is in parentheses. It'd be parenthesis e to the x minus, close that parenthesis, minus e to the negative x, close that parenthesis, and then a double parenthesis.
I just did parentheses on each side.
Some of the calculators, remember the newer ones, actually show you where the power goes up. Okay. Now, the way we do this, yeah.
Keep happening.
Barely.
For years though.
Yeah. We're going to multiply both sides by 2. Then I'm going to bring the 10 to the other side. All right. Now, this is the part where it screws students up a little bit. We want to kind of make this into a quadratic equation because we know how to work with quadratic equations, right? Well, what we're going to do, we're going to multiply everything by e to the x. Everything in there by e to the x. So when I take e to the x times e to the x, I'm going to add my exponents, which means I'm going to have e to the 2x. E to the negative x times e to the x. Well, negative x plus x would be 0. We'll get there. I'm going to rewrite it in just a second. We'll get there.
I have a question.
Yes. You just want to hear your voice on the video, is that it? All right, now, what I would do here, now, it may not look quadratic to you yet, but if we let w equal e to the x and simplify that in, we'll have w squared minus 10w minus 1 is equal to 0. Okay, and we are not done yet, so don't complain saying that we're done. I don't want to hear you moaning and groaning. I can't believe this problem's so long.
Mr. Glover?
Yes.
Can you just randomly pick W?
Yes. But usually it's either u or w, and I just wanted w this time. Now, is this factorable? Are there two factors of -1 that give you -10?
No.
No, so you can't factor it. So we're left with two options, right? One's always better than the other.
No, yep, quadratic.
So completed square is always better than quadratic formula. All right, so
Our quadratic.
now Parker, what is half of -10?
-5.
Half of half of -10 is -5. So this is where we're at so far, right? I told you there wasn't enough room. I wasn't lying. Now when we do this, we'll get to here. Now even when we solve for w here, we're not quite done because remember we let w equal e to the x. Okay, so we have to solve for x yet. Which means from here, what is w going to equal? We should be able to make this leap by now. Huh? 5 plus or minus the square root of 26. Now, we also here, we let w equal e to the x. So really, e to the x is equal to 5 plus or minus the square root of 26. Now, I want you to think back. If we were to graph e to the x here, are there any negative y values? No. So do I have to worry about 5 minus the square root of 26?
No.
Why? It's going to be negative, because the square root of 26 is bigger than 5, right? So if I take 5 minus something bigger than 5, it's going to be negative. So I really don't have to worry about this at all. I just have to worry about the plus. Now, what is the inverse of e to the x? Inverse of e to the x is natural log of x. So if I take the natural log of both sides, I'll have x is equal to the natural log of 5 plus the square root of 26. And what do you think the natural log of 5 plus the square root of 26 is? .312. It does seem like a lot of work, but you are not always going to be saying just find the answer graphically. Okay? There's going to be a lot harder problems in calculus where you have to do some different substitutions. Okay? Now, I can guarantee you on the homework assignment, there will be, let's see here. There's going to be at least one of these type of problems on homework. Okay. We are not going to work on B at this time. Now, when logarithmic equations are solved algebraic, it's important to keep track of the domain of each expression in the equation as it's being solved. A particular algebraic method may introduce extraneous solutions, or worse yet, lose some valid solutions, as illustrated in example 3. Now, when we solve the first equation in example 3, log of x squared is equal to 2, there are a couple of ways to do it. The way I like to most do it is switching from logarithmic to exponential equations. When the base is not shown on here, log of x squared is equal to 2, we know it's 10. So that means x squared is equal to 10 squared, which means x squared is equal to 100. And when you take the square root of both sides, it's going to be plus or minus 10. Now, the way that we can also do this, or that we don't want to do it, is the incorrect method. Is switching from log of x squared is equal to 2, switching that to 2 log of x is equal to 2, dividing by 2, so log of x then will equal 1. That means x will equal 10 to the first, or simply 10. We don't want this method because it does not have the negative 10 as an answer. Now, if I were to check this graphically, what we do is this. Now, the window I want to look at here, negative 15 to 15, and negative 3 to 3. Now, as you can see, we will have 2 intersection points. Of negative 10, 2, and on the other side also 10, 2. So that's how you can see that we'll have intersections, or x values will be negative 10 and positive 10. So again, be careful. Don't try and use the properties of exponents and logarithms all too much. Now when we look at b, we'll have x squared is equal to 10 to the 6th power, which means x squared will equal 1 million. When you take the square root of that, x will equal plus or minus 1,000. And there you have it. Example 4, we're only going to do the first one because it kind of ties together everything we did. Now in section 3.4, we talked about the different properties. We have log of rs to the base b, it'd be log of r plus the log of s. If we have log of r divided by s, it'd be log of r minus the log of s. So really what's going to happen is this. Because we're adding here, and we're taking two natural logs, we're going to go backwards and we're going to multiply these. And I'm going to change this one here to ln of x squared. That equals 0. Because remember, I can take this as a power. Now, what we're going to be having then, because I'm subtracting natural logs, I can simply combine them like so. Okay, all I'm doing, I'm using the properties of logarithms to combine them now. Before we expanded them, now we're going to combine them to solve this. Now, what we're going to do, we're going to take the e of both sides because the opposite or the inverse of ln is taking the e of both sides. So I'm going to take this as a power. So when you do that, we'll get this, because e to the 0 power is 1. We needed to do that. I needed to show you that step so you know that it's going to equal 1 on the other side, not 0. What we're going to do then, we're going to multiply by x squared. To cancel that out, so I have 3x squared minus 3x minus 2x is minus 5x. Plus 2 is equal to x squared.
Wait, we only multiplied by x squared here rather than on the bottom.
Correct. Now, I need to get the x squareds all on one side. So I'd be left with 2x squared minus 5x plus 2 is equal to 0. All right, I subtracted x squared to the other side. Is this factorable?
Sure.
Yes, it's factorable. So we can factor that to 2x and x. 2 and 1 equals 0. Which means x will equal 1/2 or x will equal 2. Now we do have to be careful, okay, when we graph this. This would be ln of 3x minus 2. Now, the first, I want to graph this one first. Oops. I want to graph this one first. What do you notice? What's that? Oh, I only graphed the first. I only graphed the left side. So, is it ever going to reach 1/2? No, there's going to be a vertical asymptote at x equals 1. So 1/2 can't be an answer. Okay, it's not in the domain of the left side. Now, if I graph the other one, 2 ln of x, you'll see that our intersection will be 2. So this answer is extraneous. This is our only answer. Okay. Example B is very similar to it, so we won't actually go over it with regards to time. Okay.